Allow me to guide you through a rather unusual topic, the physics connected to the memory of grandmothers who are no longer with us. The subject came up unexpectedly one afternoon. I found myself seated in the back of a taxi, sharing the ride with a young man as we moved through the city. When I happened to mention my profession as a physicist, his curiosity was immediately piqued. "If you don't mind," he began, "could I ask you a question that touches upon quantum mechanics?" I saw no reason to refuse and encouraged him to go on. He then leaned in slightly and shared something quite personal. A spiritual guide, a shaman, once offered me a comforting thought. He said that my grandmother is, in a very real sense, still alive, and that quantum mechanics is the scientific basis for this. I've always wondered, is there any actual truth to that? I had to take a moment to truly absorb the weight and nature of his question. It wasn't a typical inquiry about black holes or the Big Bang. After carefully considering his words for a while, turning the idea over in my mind, I arrived at a surprising conclusion. The shaman's assertion wasn't entirely devoid of scientific merit. However, and this is a critical distinction, the underlying principle has virtually nothing to do with the strange world of quantum mechanics. The real explanation, I realized, is rooted in a different pillar of modern physics, Einstein's groundbreaking theory of special relativity. The entire matter fundamentally revolves around the true nature of time itself. It forces us to confront the question of whether the present moment, this fleeting now that constitutes our entire conscious experience, holds any genuine, fundamental importance in the objective reality of the cosmos. It turns out that many of these profound, almost spiritual inquiries, such as the nature of existence after death, are areas where the rigorous lens of physics can offer surprising and valuable insights.
For myself, my name is Sabine Ossenfelder.
I work as a physicist and a research fellow at the Frankfurt Institute for Advanced Studies, and I've dedicated considerable thought to these intersections in my book, Existential Physics, A Scientist's Guide to Life's Biggest Questions. If we look back to the scientific landscape that existed before Albert Einstein, time was understood in a much simpler, more intuitive way. It was conceived as a universal parameter, a single cosmic clock that ticked at the same rate for everyone everywhere. We all, in theory, inhabited a shared, perfectly synchronized moment in time. There was a singular absolute now that all observers could agree upon without ambiguity. But then Einstein entered the scene and dramatically demonstrated that the reality of the situation was far more intricate and counterintuitive. The primary driver behind this paradigm shift is a cornerstone of his theory, the fact that the speed of light in a vacuum is finite. More than that, he postulated that nothing can travel faster than light, and crucially, that its speed remains the same for every single observer, regardless of their own motion. This premise might initially sound like a rather innocuous scientific rule, but it unleashes a cascade of truly fundamental consequences, one of which is actually quite accessible to our understanding. Let's put this into a practical context. Ask yourself whether the screen or device you are looking at this very second genuinely exists at this exact instant. Our immediate, gut-level intuition would confidently assert, yes, of course it does. It's right here in my hands, or I can see it sitting directly in front of me. This feels self-evident. However, we must now incorporate the profound fact we just established. The speed of light is not infinite, and information cannot travel faster than it. Therefore, every single piece of sensory data you are currently processing, every photon of light that strikes your retina, is reaching you from a tiny, almost infinitesimal moment in the past. It took time for that light to travel from the screen to your eyes. This leads to a perplexing philosophical and physical problem. How can you be absolutely certain that anything exists precisely now? In fact, what does the very concept of now even mean in a universe governed by this speed limit? This is the central, deeply unsettling dilemma that emerges directly from the framework of Einstein's theory of special relativity. Einstein himself grappled with this, attempting to construct a new robust definition of now that would fit within his theory, but ultimately, he found it to be an impossible task. To make this abstract idea concrete, let's conduct a thought experiment. Picture yourself standing perfectly still by a set of railway tracks, looking straight ahead. A long train is passing through your line of sight, moving at a very high speed from your left to your right. On board this train, precisely in the middle of a carriage, stands your friend, let's call him Bob. Now let's orchestrate a specific event. At the exact moment that Bob, from his central position on the moving train, is directly aligned with you, two powerful flashes of light are triggered, one at the very front of his carriage and one at the very rear. The crucial question we must now answer is this: did those two flashes of light occur at the same time? From your stationary perspective on the ground, The logic is quite straightforward. The light from both flashes originates from sources that are, from your point of view, an equal distance away when they ignite. Therefore, the light from both events travels the same distance to reach your eyes, and you would correctly perceive them as happening simultaneously. But now, we must shift our frame of reference and analyze this exact same event from Bob's perspective aboard the moving train. As the two flashes of light ignite, the photons begin their journey toward him. However, during this travel time, Bob is not stationary. The train is carrying him forward, meaning he is moving toward the light source at the front of the carriage and away from the light source at the back. This motion has a critical effect. It shortens the path the light from the front has to travel to reach him and lengthens the path for the light from the rear. As a direct result, from Bob's point of view, the light signal from the front of the train will arrive at his eyes noticeably earlier than the one from the back. He would therefore be forced to conclude, no, the two flashes absolutely did not happen at the same time. The truly mind-bending insight to take from this experiment is that this is the very essence of relativity. There is no ultimate arbiter of truth here. Neither your stationary perspective nor Bob's moving one is more correct or real than the other. Both viewpoints are equally valid descriptions of reality. So, what profound conclusion must we draw from this apparent paradox? We are forced to accept that there is no single, unambiguous, objective method for defining what is happening universally now. The concept of simultaneity is not absolute. It is relative and entirely dependent on the motion of the observer. Both you and Bob are right within your own frames of reference. If you follow this inescapable logic to its ultimate conclusion, the outcome is staggering. Any moment in time, past or future, could be legitimately perceived as the present by some observer moving at the right velocity. This includes all the moments from your own personal past, and it also includes all the moments that, from your perspective, have yet to occur in your future. This inability to establish a universal now that everyone in the cosmos can agree upon is a cornerstone of modern physics, known formally as the relativity of simultaneity. Its importance cannot be overstated, for it fundamentally tells us that our deeply ingrained, shared human experience of a flowing now is, from a physical standpoint, a subjective illusion. The ingenious mathematical framework that Einstein ultimately devised to make sense of this strange new reality, one that had to account for the absence of a universal now, the finite speed of light, and the relativity of simultaneity, was to perform a radical conceptual merger. He combined the three dimensions of space with the single dimension of time into a unified four-dimensional continuum known as spacetime. More specifically, because his theory demonstrated that the present moment holds no fundamental, privileged status, the logical extension is that this entire four-dimensional spacetime structure exists in its entirety, all at once. This powerful and deeply counterintuitive model of reality has become known as the block universe. Imagine it like a loaf of bread, where each slice is a moment in time. In the block universe model, the past, the present, and the future all coexist with the same degree of reality. The past isn't gone, and the future isn't yet to be. They are simply different locations in spacetime. There is just no objective physical way that you can single out one particular slice of time and declare it as uniquely special or real. Therefore, from this perspective, the past in which your grandmother is still alive and well exists in just the same way, with the same physical reality, as the present moment you are currently experiencing. There is yet another parallel line of reasoning from physics that supports the idea that individuals who have sadly passed on continue to exist in a very meaningful sense. This perspective doesn't come from relativity, but from the operational principles of all the fundamental laws of nature as we currently understand them, from quantum mechanics to thermodynamics. The core principle is that these laws do not, and cannot, annihilate information. Their primary function is simply to govern the rearrangement of the universe's fundamental constituents, all the matter, energy, and radiation. They are essentially the rulebook for how to put these components in different places with different velocities and configurations. Critically, these natural laws are deterministic and reversible. You can apply the rules just as effectively forward in time as you can backward. This reversibility has a stunning implication. If you possessed a hypothetical computer of truly unimaginable power, a machine capable of tracking the state of every particle in a system, you could, in principle, always rewind the clock and find out precisely what happened at any earlier point. In this very literal sense, information about a past state cannot be truly erased or destroyed, it is merely transformed. Now this information can, for all practical human purposes, become so scrambled and widely dispersed that it is effectively impossible for us to retrieve. Think of it like a drop of ink in a vast ocean. The ink molecules are all still there, but they are spread so thinly that you could never reassemble the drop. However, there are two significant, unresolved situations in physics where this principle of information conservation might actually be violated. These are major open questions at the frontiers of theoretical physics. The first of these concerns the information that falls beyond the event horizon of a black hole. We genuinely do not have a confirmed theory that explains its ultimate fate. The second is tied to the deeply mysterious measurement process in quantum mechanics, which seems to involve a non-reversible collapse of possibilities and also stands as one of the most significant unsolved problems in all of science. So when a person you know and care about passes away, our immediate painful reality is that we can no longer communicate with them. This loss of connection is tangible and absolute from our perspective. The physical reason for this is that the incredibly complex web of information that made up their unique personality, their memories, thoughts, and consciousness, all encoded in the neural structures of their brain, begins to disperse. It transforms into incredibly subtle and intricate correlations among the particles and energy fields within the remains of their body. These newly encoded patterns then become entangled with all the particles in the immediate environment. Slowly but surely, over vast timescales, this information radiates away, spreading throughout the solar system as heat and light, and eventually venturing out into the unimaginable vastness of the entire universe. But it's important to recognize that our definition of this information as lost is a very anthropomorphic one. It's a limitation tied directly to our own biological existence and current level of technology. Who can possibly know what the nature of consciousness or life will be a billion years from now? It's conceivable that some future form of cosmic intelligence, perhaps one that is itself vastly spread out, might be able to perceive and access these scattered correlations, making that lost information meaningful and accessible once again. So, I am fully aware that this collection of ideas might sound incredible, perhaps even bordering on the fantastical. And yet, for all we currently know about the fundamental laws of nature there appears to be something inherently timeless about the fundamental information that constitutes not only us, but everything else in the universe. I personally view this as a genuinely deep, almost spiritual insight that we can derive directly from the rigorous mathematical study of the foundations of physics. I must also candidly admit that I find it extraordinarily difficult to make intuitive, everyday sense of it. It's one thing entirely to analyze the mathematics on a page and say, okay, this is the logical framework, this is how it works. These are the conclusions that we are forced to draw from our empirical observations, and the mathematical language describes this reality correctly. It is a completely different challenge, however, to internalize this concept and make sense of it within the context of one's own daily life and perceptions. But in my capacity as a physicist, I have learned to place my trust in the methodical process of knowledge discovery that comes from applying the scientific method, even when it leads to uncomfortable or counterintuitive places. And for that very reason, I take this conclusion with the utmost seriousness. The profound implications of Einstein's theories of relativity, and about the information-preserving way that our current physical models operate, it seems to be a valid conclusion that our existence actually transcends the simple linear passage of time.